Welcome to This Explainer. Today, we're diving straight into one of the most fascinating and, honestly, one of the most secretive scientific endeavors of our time. For almost 2 decades, Microsoft ran this incredibly lavishly funded, highly classified program. We're talking labs stretching all the way from the Netherlands to Sydney. They were hunting for something they internally called the ghost particle. And their goal? To build a computer so theoretically powerful it could crack literally every single encryption system on Earth. But well, instead of a triumphant press conference, this massive multi-billion-dollar project just ended. In the dark. Internal reports were sealed up, researchers were quietly reassigned, and the whole operation was methodically dismantled without a single public word.
To really get a sense of the visceral shock of this, listen to Dr. Anil Kapoor. He's a postdoctoral researcher who spent 3 years fabricating nanowires for the project. He said, "1 month we were being told we were building the future of computing, the next month we were packing instruments into crates." Imagine that. You're standing in a hallway late on a Thursday night, looking at multi-million-dollar dilution refrigerators, equipment you've intimately learned to operate, knowing you're never going to turn them on again. There was absolutely no formal announcement, the funding just dissolved. Crates rolled in, and an 18 years scientific dream was packed away in the middle of the night.
Okay, let's dive right into this, because this is the central mystery we are unpacking today. Why on earth would one of the wealthiest tech companies in human history just abandon a massive project they once hailed as their ultimate moonshot? What could possibly go so wrong that an institution would rather completely ghost its own elite research network than publicly explain what happened? To really grasp this, we first need to understand the monumental prize they were chasing. We're talking about a machine that could theoretically break every single encryption system on the planet, including the ones guarding your bank accounts and your private messages.
To understand the stakes here, let's think about how your current computer works. It processes bits sequentially. It's kind of like a mouse in a maze that has to painfully map out every single left and right turn one by one sequentially just to find the exit. But a quantum computer? That operates on completely different logic. It basically scans all possible routes simultaneously. So for incredibly complex math, think mapping drug interactions, global climate modeling, or protein folding for cancer research, a classical supercomputer might take longer than the age of the universe to figure it out. A quantum computer? It could solve it in days.
And the secret sauce to this unimaginable power is something called superposition. Unlike a classical bit, a quantum bit, or qubit, can exist as a 0, a 1, or both at exactly the same time. When you start linking them together, computational power doesn't just double, it explodes exponentially. To put that scale into perspective for you, just 300 stable qubits could theoretically perform calculations involving more possible states than there are atoms in the observable universe. Seriously, that is not a metaphor. That is the actual physics.
But as you might guess, building physical qubits is only part of the battle. The real nightmare is keeping them alive. You see, standard qubits, like the ones Google and IBM have been building, are incredibly fragile. A stray photon, a microscopic vibration, even thermal noise from nearby atoms can cause the calculation to just instantly collapse. It's a process called decoherence. Because of this, current quantum computers require a crushing amount of overhead. You might need hundreds of physical qubits just to constantly correct errors and maintain one single, reliable, logical qubit.
And to fight that decoherence, you need extreme conditions. 15 millikelvin. That is a tiny fraction of a degree above absolute zero. It is literally colder than deep space. This is the brutal, absolute physical limit required to keep those superconducting quantum chips stable enough to just function. Because of this massive error correction overhead and that extreme fragility, Microsoft made a decision that totally stunned the physics community. They decided to walk away from the proven methods and place a massive bet on a ghost.
Part 1. Chasing the Ghost Particle, a bet against the industry.
So, to understand Microsoft's massive pivot away from the rest of the industry, we actually have to look back to a boat in the Mediterranean. Back in 1937, this genius Italian physicist named Ettore Majorana published a paper predicting a bizarre particle that was simultaneously matter and antimatter. A year later, Majorana boarded a steamship and just completely vanished. No body, no witnesses. Talk about the ultimate vanishing act. He left behind just an equation and 87 years of unanswered questions. The particle bearing his name, the Majorana fermion, drifted through physics as this mathematical curiosity. It was beautiful on paper, but totally invisible in reality.
That is, until Microsoft decided they were going to be the ones to finally capture it.
Now, you might be wondering, why were they so obsessed with this ghost particle? Well, it comes down to what's described in this incredible quote from Dr. Marcus Webb. If Microsoft could somehow coax Majorana fermions into existence at the ends of custom-engineered nanowires, they could create what are known as topological qubits. Think of standard qubits as writing a message on a piece of paper. You spill coffee on it, or hold a match to it, and the data is destroyed. But topological qubits, they store information in braiding patterns, kind of like a knot tied into the fabric of space itself. You can shake it, you can heat it up, but the knot remains. It would be inherently immune to the massive error problem that's crippling every other quantum computer out there.
Let's fast forward to 2018 and see how this builds to a climax. After years of quiet, painstakingly precise work growing indium arsenide nanowires literally atom by atom under the leadership of Leo Qualenhoven at Delft University, they thought they found it. They published this landmark paper in the prestigious journal Nature. They had observed a very specific electrical signature, a quantized conductance plateau. For physicists, this was exactly the footprint a Majorana fermion was expected to leave behind. It was immediately hailed as the smoking gun. Inside Microsoft, the mood was absolutely euphoric. The ghost had finally appeared on their instruments.
But that euphoria didn't last long. As MIT's Dr. Fatima Shaheen points out, an uncomfortable period quickly set in. Independent physicists all around the world tried to replicate the results, and they just couldn't. Some started arguing that the signature wasn't an exotic new particle at all. It could just be a super mundane quantum artifact called an Andreev bound state, which basically wears a Majorana signal like a mask. The entire physics community desperately wanted this beautiful solution to error correction to be real. But science doesn't really care what we want. It only cares about what the data actually shows.
So the crucial point here is this. It wasn't some malicious fraud. The data wasn't just fabricated out of thin air. Instead, what happened was a classic failure of motivated reasoning. These researchers were operating at the absolute extreme limits of what their instruments could resolve. The signals were incredibly faint and ambiguous. And because human beings are basically just pattern recognition machines, when you want something to be true badly enough, the patterns magically appear. They had selectively presented the data points that supported their monumental discovery and, well, ignored the ones that didn't.
And why do they want it so badly? Well, think about this number. $35 billion. That's the amount of investment poured into the quantum industry since 2015. But it's not just about corporate profit, it's heavily driven by national security terror. Every major global power knows that the first to build a fully functional quantum computer can theoretically decrypt the military communications of their rivals, not to mention your encrypted texts, your passwords, your entire digital life. When national prestige and personal privacy are all on the line, that immense pressure can really distort the line between a genuine scientific discovery and the wishful interpretation of ambiguous data.
When the reality finally set in, the fallout was devastating. In 2021, that landmark Nature paper was completely retracted, and it later surfaced that junior researchers had actually raised red flags about the data internally, but they were entirely sidelined or ignored. The foundation cracked, and Microsoft initiated a silent, methodical shutdown. Contracts were quietly canceled. Equipment was packed into storage. Brilliant PhD students and postdocs who had structured their entire academic identities around this project were left completely stranded. Their defining early years were wiped out without so much as a press release. It really seemed like the definitive end of the road. Until it wasn't.
Part 2. A Cautious Resurrection, the 2025 return of Majorana.
In early 2025, Microsoft suddenly made headlines again, announcing the Majorana 1 chip, which was a stunning resurrection of their original bet. They claimed it incorporated a brand new topological superconductor material, but the triumphant certainty of 2018, that was long gone. This time the announcement was highly cautious, completely filled with layers of internal verification and redesigned measurement protocols. And yet, as Yale physicist Dr. Priya Natarajan notes, belief is not evidence. The fundamental issue remains. The Majorana 1 chip is proprietary, and the detailed experimental data hasn't been made public. What the community desperately needs is independent replication by groups who have absolutely no financial or reputational stake in the outcome. Until then, the scientific verdict remains suspended just past the edge of what anyone can independently confirm.
Which leaves us with this final, profound question. How do you know if you are in a dead end, or just taking a very, very long detour? The Majorana fermion has been chased for nearly 90 years now. But remember, the LIGO project searched for gravitational waves for 40 years before they finally heard two black holes collide. The universe is under no obligation to cooperate on a corporate roadmap or a funding timeline. The ghost particle might still be out there, embedded in the fabric of space, just waiting for instruments sharp enough and researchers honest enough to see it clearly. Until then, what else don't we know? Thank you for joining me for this explainer. Keep questioning everything.